Alright, I got a fully new setup. We got new camera up there, and we got mic down there now. Mic down here now. So hopefully things will be better. Okay, so chemistry, we are going to talk about acids and bases, and pH, pOH, and all of that. So first let's begin as if we didn't even know what an acid or a base meant. So an acid is any type of liquid, normally based on water, that has a higher concentration of H pluses than concentration of OH minuses. So this would be acidic if we have a high concentration of H plus, low concentration of hydroxide. I'm gonna call it hydrogen versus hydroxide. Just because that makes it easier to say. I may say H plus, I may say OH minus, but that's what it is either way. And just know that also H3O plus concentration is the same exact thing as H plus concentration. It just depends on how you talk about it. So an acid is anyone that has a higher concentration of H pluses in solution and a lower concentration of OH minuses. So literally what that means is that if you have a solution, like you're inside of a bubble of water, and you have, let's say we have H plus, H plus, H plus, OH minus. So this would be significantly more acidic than basic because there are more H pluses. It's as simple as that. And just so you are aware, acids taste sour. They typically would taste sour, and you know that because of lemonade, or like lemon water, because that what makes lemons really sour is acetic acid. Um, so an acid. Okay. Now I'm gonna erase this, just this part. So now if we talk about a base, it's just the opposite. It would be a lower concentration of hydrogen and a higher concentration of hydroxide. So again, all that literally means is we have OH minus, OH minus, OH minus versus H plus, where we have more OH minuses than H pluses in our solution, in our little bubble of water. So this would be basic. And bases typically taste bitter. So like if you've ever had pH water that didn't have like added electrolytes, it tastes disgusting and it's bitter and gross and leaves your mouth drier than it actually started out. So glad that I got me some Crystal Geyser because it's just better. So let's classify some acids and bases and make it easier to describe stuff. So there are two main leading theories as to what makes an acid and what makes a base. One of them is called Arrhenius, and one of them is called Brønsted-Lowry. Those are the two main ones, and those are the people who thought of them. So Arrhenius acids and bases are all dependent on whether or not the thing adds or subtracts H pluses or OH minuses to solution. It just depends on whether or not the thing actually produces, like, I'm going to use a different color. If H plus concentration goes up, then this is an acid. If OH concentration goes up, then it would be a base. That's kind of your difference. So to give an example, let's say we have, nice please, cord. HCl would be a good example of an Arrhenius acid, because what you would have when it disassociates is H plus plus Cl minus, which would be a definite example of an Arrhenius because it directly increases the concentration of H pluses. Now, to give another example, we'll have NaOH, so sodium hydroxide, which would form H plus plus, H plus, yeah. It'll form Na plus plus OH minus, which would make it definitely an Arrhenius base because it's directly producing OH minuses. Now, to give examples of Brønsted-Lowry, it's all about the transfer of protons. It's all about the transfer of H pluses in solution. So whether or not things are giving or taking H pluses makes them Brønsted-Lowry acids or bases. Normally, when you talk about Brønsted-Lowry acids and bases, you talk about them when they react with one another in solutions as opposed to when they dissociate. So for example, you can talk about it like this. HCl plus NH3 forms Cl minus plus NH4 plus. So this here would be an equation between hydrochloric acid and ammonium to form chloride ions and ammonium. So what's happening here is this HCl is giving an H to the NH3, because in the end we're left with one extra over here and that one minus there. So because this one gives away its H+, this here is your acid, which I'm going to represent with A. This here, because it accepts the H+, is your base. You would represent that with B. Okay? Now, on top of that, there's also another category of how things work inside of this, which represents the products. So now, let's say for a minute we just zoned in on the products. Well, let's see what has the capacity to do what now. So the ammonium has the capacity to give away another H. The chloride has a capacity to take another H. So because the chloride can take an H, that makes it a base. Because the NH4 plus has the capacity to give an H, that makes it an acid. So because now we're talking about it in terms of HCl and NH3, you would have a conjugate base and a conjugate acid. So that word there, conjugate. And the thing is, the conjugates for these things will always stay constant, which means the conjugate of hydrochloric acid will always be a chloride ion. So you'll have an acid form a conjugate base. The conjugate of ammonia will always be ammonium, turning a base into a conjugate acid. Notice how every single time we have a base that becomes a conjugate acid, and then an acid that becomes a conjugate base. I mean, it only makes sense, because if you give up your hydrogen, now you can accept a hydrogen again, which would be the exact opposite of what you just did, making you the exact opposite of what you were before. So now one more thing as well. When you switch between these things, strong acids will produce weak conjugate bases. Strong bases will produce weak conjugate acids. Now let's say we wanted to rank the strength of all of these things. So we know just from our own experience that HCl is a strong acid, which I'm going to represent with an S. So we know that that's a strong acid. If a strong acid has its own conjugate base, which it always will, that means that you'll form a weak conjugate base. It'll always be the complete opposite. So a strong acid produces a weak base. I mean, it only makes sense because HCl only goes towards Cl minus plus H plus. Now, of course, there's going to be some variation of this that's going backwards, but the second it forms, it'll split away again, because that's just how it works. So that would make Cl minus a really horrible base to want to put in solution, which makes it not a base. It actually just makes it neutral. So that's kind of how it would work. So it would be a really weak base. And then now let's compare with this NH3. NH3 we know is a weak base just from our own previous knowledge. Because this is a weak base, that makes NH4 plus a stronger acid. It would be a stronger acid than, it would basically be, the NH4 plus is stronger at being an acid than this is stronger at being a base. Because NH4 plus isn't necessarily a strong acid. It's a weak acid, but it would be stronger at being an acid than this would be at being a base. It's still nonetheless weak, because the equation between NH3 would be what? It would be NH3 plus H2O forms NH4 plus OH minus, with an equilibrium expression, which means you can flip this if you wanted to, which would make it still weak. So normally what you'll just have to know is that a strong acid produces, or strong anything produces a weak conjugate. Acids produce conjugate bases. Bases produce conjugate acids. It's just literally all opposites when you switch from reactant to product. And that would be just how the Brønsted-Lowrys work. Now, let's talk about making equations with both Arrhenius and Brønsted-Lowry stuff. Let's say, for instance, that we wanted to represent an equation that would often be used for Arrhenius stuff, and that would be a neutralization. So this would be an acid-base neutralization. Basically, what would happen is we would have a base that's in solution and an acid that's in solution. Kind of similar to this one, except without the whole Actually, you know what? It probably would be very similar to that one. So let's just say we're doing HCl plus NaOH. We'll have HCl plus, I want to do CaOH, because that would make this a little bit more interesting. I'm going to pretend like I'm writing all the, this is a solid, this is an aqueous. I'm going to pretend like I'm writing all that, but I'm not, because it just makes it take longer. That's not equilibrium. So basically, sometimes you'll be asked, what's the acid-base reaction that forms the salt calcium chloride? Well, here's what you would do if you wanted to do that. You would create your acid out of the calcium, or acid out of the chloride, because chloride would be a Cl minus, which means you would need to add H pluses to it to make it an acid. And then the calcium is the opposite. You need to add OH minuses to make it the other thing, because it is CH2 plus. So, or Ca2 plus. So that would mean then that you would form CaCl2 plus H2O. So if you're forming two Cl's, you need two of these. If you have two hydrogens there and then two there, that would mean two waters. So now we have our equalized thing. If we wanted to add the Brønsted-Lowry attachments to it, we would go, this would be A, this would be B, this would be neutral, this would be neutral. Just because that's how neutralization stuff works. So now if we wanted to do another Brønsted-Lowry example, let's do this one. Let's do it between acetic acid. So we'll do CH3COOH plus a base NH3, which would form CH3COO minus plus NH4 plus. There we go. Where we have a transfer where this H goes over there, which would then make our CH3 COOH, because the Brønsted-Lowry tells us that things that donate are acids. This would be an acid. This would be a base because that's what's accepting it. This here would be a conjugate base because it's the opposite of an acid, so it becomes a base, and because it can now accept an H+. This thing would be our conjugate acid because now it has the capacity to give another H+. And because it's the opposite of a base. So there we go. That's the classifications for Arrhenius and Brønsted-Lowry and what all of those mean. Now let's talk about how we would actually apply these and what these actually mean. So first I'm going to take a holistic view on what these equations mean and what pH actually is. Hello, auto adjust. Hey, new camera. You might see that every once in a while because auto adjust. So let's talk about what pH and pOH are. So basically scientists needed a representation to show how acidic or how basic, basically how many more H pluses or how many more OH minuses there were in solution. So they came up with this system. They came up with a pH scale. First of all, you need to know that a pH scale or the pOH scale are both, they're logarithmic scales, which means that as, let's say we move from 8 to 7, that means that we're increasing or decreasing a concentration of a certain amount of things by a factor of 10. So that would mean we would go from 10 to 1. Like that. So if we went from 8 to 5, let's say, that would be going from 1,000 to 1. So it's a logarithmic scale. And because it's way easier to scale things based off of numbers instead of logarithms, also way easier to write them, we base them on logs. Played with the settings a little bit on the camera to try to get it to stop auto adjusting because there was an entire segment that I couldn't keep because it was entirely blurry the entire time. So I'm going to try to pick up where we left off. We started talking about how the scale actually works and where those numbers come from. So basically though, if we want to shift things to make them equal, so normally a logarithm has a scale that goes something like this. And it's important to note that typically the concentrations we're dealing with H pluses and OH minuses are really small, like really, really small. Definitely below 1, between 0 and 1. So what they do is they basically, so that it knocks out two problems at once, it makes it easy to talk about scale and then also at the same time giving us a workable number. What they'll do is they'll hit it with a logarithm so that it flips it up and gives us a y value of some number, typically between 0 and 14, and you'll see why that is in a minute. typically between 0 and 14. Then what they'll do is they'll hit that with a negative, because when you plug in a logarithm like this, notice it's giving us all negative numbers. So we just hit it with a negative logarithm, and then now we have a positive number between 0 and 14, where every single time we increase in the number once, we decrease in the concentration of H+. Hence why acids are on the lower spectrum and bases are on the higher spectrum. Because if our pH is low, then that means we have a high number. If our pH is high, we have a low number for H+. So, with that being said, now we've made up a scale that we can rank how much H+ and OH- there is in a solution. Now notice that these are kind of just the opposites of one another. And that if we wanted to go instead from we're given pH and we want to find the exact concentrations, we can just hit it with 10 to the power of negative pH, because that would just be the opposite of a logarithm. Okay, now the next thing we need to know, this is important. So pH plus POH is equal to the negative log of the dissociation constant of water. So this is just another K value like we've done for a while, because water, H plus OH minus, is in equilibrium with just basic water. Now, there's a second way this is written. H3O plus OH minus is 2 H2O molecules. That's the second way you write that. But I'm going to write it this way. I'm rarely going to use H3O. Although there are some instances later that you'll see that you need it. But because water is in equilibrium with its ions, you can represent it. You can represent the tendency for something to be present, whether it be products or reactants. I think that should be switched around, actually. The tendency for one to be present based on an equilibrium constant. So if we want to find the total pH in anything, what we'll do is we'll add pH plus POH, and we'll get negative log of that. Which kind of makes sense if you think about it, because pH would be negative log of H plus, so really minus negative, or minus log of OH minus would give us negative log of KW. I don't know why I put brackets in there. Which makes sense, because that's how adding logs works. Because what KW is at the end of the day is it's going to be the reactants, it would be the products, because I wrote that equation backwards. It would be H2O turns into H plus OH minus. That would be our equation. So we have H plus OH minus is equal to KW. So that would be the equilibrium constant of water. We have H plus OH minus. Now, if you have H plus OH minus, that would be like saying negative log of H plus times OH minus, which is just like saying this. That's just the same exact thing. So now that we have an actual equation to represent how pH works, we also know on top of that that KW at 25 degrees Celsius, I'll explain why we're doing 25 degrees Celsius, is equal to 1 times e to the negative 14. So KW at 25 degrees Celsius is 1 e to the negative 14th, which means that pH plus POH at 25 degrees Celsius is equal to 14, because that's just what you get when you plug this in for that. So why 25 degrees Celsius? Well, it spits out a really nice and easy number. And second of all, 25 degrees Celsius is very convenient, because most solvents that you're going to be using in chemistry, like literally any chemistry classes, most of them have freezing points that are below 25 degrees Celsius and boiling points that are above 25 degrees Celsius, which means it's a perfect middle ground between all the freezing and boiling points of random solvents that you would use. Like, we can't exactly do 0 degrees Celsius, even though that would give us standard temperature and pressure, because 0 degrees Celsius water is not water, it's ice. And you can't really dissolve anything in ice. At least not nearly as well as you can with water. So we do 25 degrees Celsius because it's a nice and easy number for a lot of different solutions. Now let's talk about how we would actually calculate this stuff based on concrete numbers we'd get from actually making solutions. Let's say we have a problem here that says that we have 0.015 color change molar of hydrochloric acid at 25 degrees Celsius. Okay, so we want now to find H plus, OH minus, pH, and POH of this whole thing. We want to find it of everything. So first of all, let's talk about what HCl is really quick. So HCl is an important compound because it's a strong acid. That means that it'll completely disassociate when you plug it into water. Hopefully I'll have an animation running over this because I animated this part. It'll completely disassociate when it's in water. So that means it'll just completely separate, and however much HCl you added is exactly how many H pluses you're going to be left with when you add it to solution. Why exactly chemically does it completely separate and HF doesn't? Who knows? We will probably find that out way later in the year, either then or in college if you actually go and pursue chemistry, but we'll see. So for our intents and purposes, though, we just want to try to find the pH of this. Like, the ultimate end goal is finding pH. So we know that this will split into Cl minus and H plus. So any amount of molar of this is going to be the molar of those two. So that means we'll have 0.015 molar of H plus as a result of this. So, and then we can just, if we want to make it concrete, as if we're answering a free response question on the AP test, we'll just do this. HCl turns into H plus plus Cl minus, and then you do molar ratios. And then you would stoichiometry it. But I'm not going to do that because I don't want to waste our time. So we have 0.015 molar of concentration of H plus, so that would be our answer there. Okay, now we'll take the water equation into account, because once we've gotten things into concentration of H plus or OH minus, once given a concrete number, then you can start playing around with the water one. So we will have H plus times OH minus equals the KW at any one point. Or it equals this negative log KW, but if you remember, at 25 degrees Celsius, KW is equal to 1 times e to the negative 14th, which is just like saying the pH, if you add the two up, is equal to 14 at any one point. So that means the concentration of this is this, 1e to the negative 14th, pH plus POH is equal to 14 for this whole thing. So these will be important equations that we need to know. I believe they are on the equation sheet. This equation, though, I'm going to bring it up close to the camera. This equation, though, you might want to memorize. Because it makes it way easier to know exactly what the pHs are given a KW. So let's plug this into here. So we have H plus, so we'll go 0.015 times OH minus is equal to 1e to the negative 14th. Now that's this in here. So we have 0.015, or no, 1 e to the negative 14th divided by 0.015 is equal to concentration of OH minus is equal to 6.67 e to the negative 13. Okay, now we have concentration of OH minus. Now, because the rest of it is rather simple, I'm just going to actually move this over here because these are the only ones I'm going to be using after this point. So let's go and do pH now. So we know pH is equal to negative log of H plus. So that would mean our pH here would be negative log 0.015 is equal to, please, 1.823. So normally when doing pH, we're going to round to the hundredths place. So let's do 1.82. Okay, so that would be our pH. Now remember how we said that the lower number you go when you're on the pH scale, the lower, the more acidic? Well, that makes sense because this is a strong acid. This is a very low number. Okay, now let's do POH. Two ways to get there. You can get there based on this equation, which is what I'm going to use here, or you can get there based on this equation, but just saying OH and then OH minus instead. So we'll do POH plus pH is equal to 14 at 25 degrees Celsius, specifically 25 degrees Celsius. So 14 minus answer, please focus. Hopefully you can see it, because I turned off the autofocus, which means now it will not like shutter and give me bad video, but then at the same time you can't see my calculations. So 12.18. So that means our POH is equal to 12.18. So when you're on the POH scale, everything just flips around. Low numbers equal strong bases, and high numbers equal strong acids on the POH scale. So obviously, again, this is a strong acid. It should have given us redundant results. Now, I would get used to. I would like highly recommend getting used to putting things in pH and then understanding things in the perspective of pH. And then kind of just knowing POH is the opposite of pH and basing your knowledge on pH, because that's what's used. pH is the thing that's actually used. POH is kind of this side thought. Got him. So now what we're going to do is we're going to try to do the exact same thing, but at a different temperature. So let's do this now. I'm going to erase everything except for this part, because the pH does change at a different temperature. Let's say that now our solution is 37 degrees Celsius. And every single time they change the temperature on you to where it's not 25 degrees Celsius, they'll give you the KW. I'm pretty sure they won't give you the KW, though, if it is 25 degrees Celsius. You just have to know that KW at 25 degrees Celsius is 1 times e to the negative 14. So we have now 37 degrees Celsius, KW is equal to 2.56 e to the negative 14th. I don't write the times 10 because I don't like to. So just know that that e is the same thing as scientific notation. I just write it the same way your calculator does. So now that we've got this doesn't change because that's just a constant based on how much stuff we're adding, because it's, again, a strong acid. So now KW is equal to this, which means that pH plus POH, this is the equation I told you need to memorize, is negative logarithm of KW. Don't know why I put that bracket again. So that means if we plug this into our calculator, pH plus POH is equal to whatever this number is plugged in for that. So let's go negative log, try to put it away so I can make sure that you guys can still see what's going on. So that means if we raise the temperature a little bit, that pH is going to drop slightly, or at least the maximum pH will drop. So we'll now have 13.59 is going to be our new number that we're going to base everything off of. So now what we're going to do is we're going to go pH is equal to negative log of the concentration of H+. That doesn't change. So that means pH, again, is just going to be 1.82. But now POH changes because our concentration of H, or OH minus, is going to change because, again, our KW changed. So that means that if pH is equal to this, we're going to plug this back into there, and then we're going to get 133, yes. 13.59 minus 1.82 is equal to 11.77. So that means POH is equal to 11.77. Now, what's really nice about calculations for pH and POH is there's always two ways to get there, because the entire thing is a square of equations that are all reverses of one another. So that means if we want to check our work for this POH, because this number looks different and weird, we can just plug this POH back in. We can do this. Concentration of OH minus has to be equal to 10 to the negative power of the POH. So let's test that out. 10 to the negative 11.77 is equal to 1.70. So OH minus is equal to 1.70 e to the negative 12. And now we can test that here because we know that Kw at any time is equal to OH minus H plus, because we know that that's always true. Let's just plug our Kw and our H plus in and make sure we get the same number here, because this should be the answer. If we get a number super close to it, that would be good, because we're not going to get the exact same answer, because again, this pH here is a rounding estimate. So we should get a number very close. So that means that if we do Kw 2.56 e to the negative 14th divided by our H plus 0.015, we should get a number very close to that. 1.7066. Yeah, very, very close. So that means we are just golden with that. Okay. That is the basics of calculating pH with a strong acid. Now let's move to weak acids. Weak acid time. So 0.015 molar of hydrofluoric acid with an equilibrium constant of 6.9 times e to the negative 4th. I think that's what the number is. You know what? No, it's not the number. I lied. It is 7.2. Just remember, it sometimes changes with temperature, but I want to get this one right when it's at 25 degrees Celsius. At least, hopefully. Hopefully that's what it is. So, at 25 degrees Celsius. Okay, now really quickly, before we go on, we're going to actually talk about what it actually means to be a weak acid. So a weak acid, like hydrofluoric acid, is going to have an equation of HF turns into H plus F minus, going back and forth. So let's say, for instance, we have a crystal of it about to be dissolved in water. That means some of it will go back and forth from being a solid to being dissolved, and then some will go back and forth from being dissolved to solid at equal rates of one another when they're at equilibrium. So they'll just go back and forth, kind of like how this animation represents. Just know as well that strong acids and weak acids do the exact same thing as strong bases and weak bases, just with different molecules. And we want to calculate the pH. So first of all, hydrofluoric acid is a weak acid, hence why we're even doing this problem. Which means we got to go through an ice table to try to find the concentration of H+. Because that's what we need to find pH. So I'm so sorry, we have to go through an ice table. HF is going to react to form H+, plus OH minus, yeah, right. F minus. So that's our equation for it. So now we'll go ice. I'll do little brackets to represent that we're talking about concentrations. I put dotted lines around here because that helps me organize my data. You can do what you want. So 0.015 initial, 0 and 0 initial. This would be minus x initial. This would be plus x and plus x initial, or change. And then we'd have x, 0.015 minus x at equilibrium. So now Ka, you probably noticed that Ka by now. So Ka is different than Keq, but at the exact same time, it's the literal, like, it's the exact same thing. So all that A represents is now we're talking about an acid. We're talking specifically about an acid. If you were talking about a base, you would see Kb. They mean the exact same thing as any other time we've seen the letter K before. And then that W for water means water. So again, it's just the tendency for an acid to want to ionize. Now let's go ahead and solve for it. So we have Ka is equal to product over reactants when they're all multiplied. So that means we're going to have 7.2 e to the negative 4th. I trust that you know the equation already. Is x squared over 0.015 minus x. Because I don't want to write it again because it's redundant. So now really quickly, if this is bothering you, I'm going to explain why. When I say bothering, I mean how it's not going all the way over. The AP test tells you that at least for this year, 2022 to 2023, that you can remove this minus x because you can assume that that minus x is really small, or at least like insignificantly small for the problem you're dealing with here. why you can even do that is because they want to test you, the AP graders want to test you on your ability to do chemistry, not your ability to do algebra. And this would be some intense quadratic equation nonsense that we don't need to deal with, where we'll get an answer of something insane. Now, if you have a graphing calculator, go ahead and go for it. Just plug this in for 0 is equal to x squared, 0.015 minus x, minus 7.2 e to the negative fourth. Go ahead, eat your heart out, hate. So what the AP test graders tell us we can do is just erase that minus x. Right there, and then we'll be left with just one x term that we can really easily solve for the answer for. So now let's go ahead and plug it in. 7.2 e to the negative fourth times 0.015, and then hit that with a radical because we have x squared. So that would be equal to, x is equal to 3.29 e to the negative third molar. And now because the concentration of H plus at equilibrium is equal to x, we have H plus is equal to 3.29 e to the negative third. Okay, that's H plus. Now let's go for pH. We're not going to go to OH minus because it's, again, redundant. We're at 25 degrees Celsius. It's just the simple KW is equal to OH times H equation. So we'll do this. pH is equal to negative log of the concentration of H plus. So we'll go negative log 3.29 e to the negative third is equal to 2.48. So pH of this specific thing is equal to 2.48. Now, just so you know, this isn't the actual pH of hydrofluoric acid. I think it's just because we added a lot of it. Like this would be a lot in comparison to any other solution you're making. This would be about a little less than a gram. Normally you're not doing that much, because the normal pH of it is around 3.17. There's a bajillion reasons why we would have gotten 3.17. Like for instance, if that x wasn't negligible, we would get a different number. And we're just going to say, for our own sake, that it is. You'll notice that this x value is actually e to the negative third, which isn't insignificant here. That would be like saying we're cutting off a number at this decimal place, which is significant when you're talking about logarithms. Because, again, logarithm graph looks like this past 1. That's a pretty big spike right there. But, for the most part, AP test tells us we can take a shortcut, so we're going to take a shortcut. Okay. Now, really quickly, we're not done. We're going to discuss one more thing. We're going to discuss why KW changes depending on temperature. So, here's the dissociation equation for water. H2O, or at least one of the two. I'm going to use this one, though. H plus plus OH minus, okay? So KW at 25 degrees Celsius is equal to 1 e to the negative 14th. KW at 37 degrees Celsius is equal to 2.56 e to the negative 14th. And then here's one more, just so that we can do it. This would be at 100 degrees Celsius. Don't ask how you have liquid water at 100 degrees Celsius. KW is equal to 5.13 times 10 to the negative 13. So, you'll notice a trend here. You'll notice that as you go greater in temperature, you increase KW. So as temperature increases, KW increases. So what does that actually mean for our equation here? Well, that means that KW is equal to products over reactants. So if KW is increasing, now here we go with the whole variable stuff. If KW is increasing, then that means that the products must be increasing, the reactants must be decreasing, or both. Because that's the only way you can manipulate this equation to make this increase. So that means that products are increasing, reactants are decreasing with this equation, and this equation is not flipped, as the temperature goes up. That is really significant because that tells you that the dissociation of water is either exothermic or endothermic. It's dependent on temperature. Now, which one is it? Well, let's just try to add energy into this equation somewhere. Let's just try to plus E it somewhere. So we'll go plus E or plus E, and then we'll kind of just do a little thought experiment to figure it out. Well, if temperature goes up, so that means if you add heat, if you add energy to it, you're going to see an increase in products. Well, Le Chatelier's principle tells us that if we increase one side, the other side is the thing that increases. So that means if we increase heat and then we increase products, that means that our energy has to be on the reactant side. So that means that the dissociation of water is an endothermic reaction, because it takes in heat and transforms that into more dissociation, more ions, which, if you think about it for a minute, what you're tasting in water is the ions inside that water. Hence why whenever they say like added ions, something like that, the water tastes different. And when I say added ions, that time normally it's salts. It's not H plus or OH minus. That makes it taste different. But that's why warm water tastes different than cold water, because more energy has been added to it, meaning more H2O has split up into more H pluses and OH minuses. And we said before that H pluses are sour because acids are sour. OH minuses are bitter because bases are bitter. So that means water has a stronger taste, either sour or bitter. Who knows? You all know what taste I'm thinking of right now. That we're going to get more ions because you taste the ions when the water's warmer. That's why I'm glad that I have a cold water here, because God, I hate ions in my water. It makes it taste disgusting. So that there is why water, or why the KW changes when temperature changes. And that's also important because there are almost no equations in existence that don't operate with some bias towards heat, either on products or reactant side. And then that means that the Ka or Kb of any acid or base, or really any equilibrium expression, like forgetting acids and bases for a minute, is going to change based on E. So that means we have to assume that things are at 25 degrees Celsius if they give us an equation like this, without specifying a different KEQ. And they'll always give us it if it's different, always, except for this one. This one they will not give us because that's 25 degrees Celsius. Okay, now we will talk about the special cases and things that aren't as simple as HCl and HF. We're going to talk about different kinds of molecules now. Okay, first of all, I'm going to color code all of these a certain way. The acids are going to be red, the neutrals are going to be green, the bases are going to be blue, and then the ones that can act as both acid and base are going to be purple. So firstly, we have polyprotic acids. So just as an example and kind of a layout for all of them, at the very top left of all of these is going to be the basic structure of one of the represented molecules of this type. And then either below it or to the side of it, because the amines one needs a lot to fit it, below it, most likely, is going to be all the examples of other kinds or specific examples of some sort. Something like that would be the basic trend. So in this one, we have sulfuric acid, so strong acid, and that's the basic structure. You see that sulfur in the very middle with oxygens at the top and bottom. And just so you know how these actual structures work is 1 dash means a single bond, 2 dashes means a double bond, 3 dashes means a triple bond, and those are basically going to be the only kind of bonds we see. You may see a dashed line bond as well. Dashed line typically means hydrogen bond, so it's a much weaker bond than normal, but I don't use dash bonds because here they are covalently bonded. So we have a sulfur with 2 double bonded oxygens at the top and bottom, and then 2 single bonded oxygens at the left and right. Attached to those single bonded oxygens is another hydrogen molecule. So you can kind of see how the molecule gets its structure and why certain things are a certain way. The cations, the H pluses, are going to be attached to the very left and right side, and then the SO4, that anion, is its own group and doesn't dissociate because it just all stays together. It's all one group. And most molecules, well, actually almost all molecules, have a structure that's very similar to this, where if they have somewhat complicated structures, it's because there's one main group and then a little other few parts that are attached to it. So then at the bottom, or beneath that, so the left middle one, we have bisulfate, which is basically just what happens when you detach one of those hydrogen molecules. So one of them will come off, or hydrogen atoms. One of them will come off, so then you'll be left with a negative charge on one of the oxygens, and then the other will stay as if it never changed. And because this is sulfuric acid, it's going to be a rightward reaction favoring products way over reactants because it's a strong acid. And then you go and do it one more time, and you're left with just that sulfate group in the middle. So now it's just sulfate with two negatively charged oxygens on it. And then again, because it's a strong acid, it'll be a rightward shifting one. But no, if this was a weak acid, the strength at which you'll have to add more energy in order to detach more hydrogens. So let's say it were phosphoric acid, which is H3PO4. And because it's a weak acid, you'll take some effort to take off the first one, more effort to take off the second one, and the most amount of effort to take off the third. And that's just how normal chemical bonds go. So the notes, now I'll go through the notes. Polyprotic acid means many protons. Since a single H plus would be a proton, because a normal hydrogen is just a proton and an electron, but H plus means that electron is gone, so it's literally just a proton. So polyprotic, as in many protons, and then acid because it's an acid. So polyprotic acids are characterized by how they can donate more than one H plus. That's just polyprotic acids. And then the more H pluses are pulled off, the more energy it takes to remove the rest. Yep, that's true. Sulfuric acid's a little bit of an exception. It does take a little bit extra energy to pull off that second one, but it's almost unnoticeably small because, again, it's a strong acid. And then H pluses for polyprotic acids must be detached in separate steps, one by one. Otherwise, it would be incorrect. Let's clear my voice here. Hello. So that fifth one would be, and this is the long one, when writing the chemical equation for its dissociation, it is acceptable to write everything in one step. But if told to write steps, all steps must be in separate equations. So if you're just looking for molar ratios, you don't need to go and split it up for steps every single time. But if they're asking what are the dissociation steps of H2SO4, you're going to have it shown like the two equations on the left side, or you're going to get your points off. And you need to show both equations. And then just a little note, bases don't detach their OHs this way. Everything detaches at once in a base, just because that's how the chemical works. So like let's say you had calcium hydroxide, which would be Ca, and then two OH groups, two hydroxide groups. The way that one would work is in one step, all of the OHs would come off when it's in solution. They don't come off one by one. That's just the chemistry and the chemical physics of how that one works. So that, in essence, is polyprotic acids. Our second special thing is carboxylic acids, which have the chemical formula of an R group and then COOH. And then our example is going to be acetic acid, which is CH3COOH. Basically, judging off that top left one, our chemical structure is an R group and then COOH, which is governed by that molecule right there. So basically we have any R group where that R is normally an organic compound. I'll talk about what that means a little later. And then we have a carbon that it's bonded to, which is bonded to an oxygen that has a double bond, and then another oxygen with a single bond with an H attached to it. That H is going to be what normally pops off when it is dissolved in water. To give any example, we have acetic acid, that middle one. So basically that R group just turns into the CH3, which is just that C with the 3 H's with single bonds bonded to it. Then with an equilibrium reaction, we get CH3COOH, because again, this is a weak acid, turns into acetate and then a hydrogen ion. So we're just left with the same exact thing as that middle one, but just without that H that I said previously popped off. If you remember it that way and just remember that those slanted parts are the parts that you need to actually make this a carboxylic acid, then it makes it pretty easy to visualize what's going on. Okay, now our notes. So organic acids, typically only C, H, and O. That's your kind of key. That's your key. Is if it's organic, it'll normally have only C, H, or O in it, with the occasional N or P. Those are the typical things you would see in organics. But for this instance, we're mainly going to deal with C's, only C's and H's really, because if you add other stuff to it, it becomes something else. And you'll see what that is later. Made of an R group, which is the organic part, and then a carboxyl group, which is the COOH. Okay, and then they're always weak acids. You won't ever really see these strong acids. I don't think any of them actually exist. And then the conjugate is called a carboxylate base. So it's not a carboxylic base, it's a carboxylate base. And then that's just because it can now accept an H plus and turn the solution less acidic. Like just to give some examples, we have fatty acids, and then there are some amino acids that are carboxylic acids. And then a good note to remember for this is acetic acid specifically, the one that's shown here, because it's vinegar. It's a very common substance. That's carboxylic acids. And now we will talk about alcohols. The one that's shown here is going to be methanol, not the one that you drink. Ethanol would be the next one up, which is C2H5OH, which would be the one that you would drink. So alcohol, you'd see an R group, an organic R group, and then an OH attached to it. So this looks very similar to a hydroxide like we've seen before. It is very similar to a hydroxide like we've seen before. But the thing is, the R group that's attached to it isn't just some random cation. It's specifically an organic cation. Again, C's and H's are the typical ones you'll see. But then there's also the possibility of O, N, and P. We actually call that a hydroxyl group instead of a hydroxide group because it acts differently when it's in solution like this. So your example is that really simple molecule, R bonded with O bonded with H, and then your CH3OH methanol is that like sideways cross looking thing. So these are organic molecules, going to our notes now. So typically only CH and O again, made of an R group and then a hydroxyl group. So alcohols are special. They are neither acidic nor basic. They're actually neutral solutions. So if you ever see an alcohol, it doesn't have dissociation equations. It doesn't do any of that because it's not acidic nor basic. It'll just stay as it is. Because alcohols themselves are more so solute. Like they are solvents. You don't really use them for actual synthetic chemistry often, but occasionally they are used because you can break them apart. But typically they're used as solvents. They also tend to not break down molecules as quickly as water. So if you don't know, vanilla extract is like 50% alcohol because the chemical that makes vanilla, called vanillin, doesn't break down as quickly when it's in a concentrated solution of ethanol as opposed to being in just pure water. It doesn't break down as quickly, so it has a longer shelf life, and then often that alcohol just gets burnt off in the cooking process, whether you're making pumpkin pie or cookies or something like that. It'll burn off when you cook it. So they'll do it in ethanol because it makes the vanilla last longer. So that third note is it has no dissociation equation or conjugates since it's neutral. I mean, duh. And that would be alcohols. Okay, first of all, oh my god. There's a lot of things going on here. These are the amines. I promise you it's not as difficult as I made it look. It's just I wanted to give as many basic examples as possible because that makes it easier to visualize what's going on when you have the basic examples, because there are different kinds of amines, but really we'll only deal with the primary amines. So let's get into exactly what amines are. Amines are an R group. Again, this would be organic, bonded with a nitrogen, and then any amount of hydrogens, either 2, 1, or 0 of them. Typically, we're only going to deal with the ones that have 2, but the ones that have 1 have popped up before, and I'm sure the ones that have had 0 have also popped up before. So basically, let's look at that top left one. So RNH2, that would be a primary amine. It's basically just the same type of thing we saw earlier, except you have 2 hydrogens bonded to a nitrogen, which is now bonded to your R group. I labeled this one R1 because sometimes they can change the R groups. They don't necessarily all have to be equal, and that's what makes amines kind of special, is that they can vary on many different fronts. So then that first example, CH3NH2, methylamine, is just H3C bonded with the N and then the H. Notice that this time I didn't separate the bonds between the carbon and hydrogen, because that would have made this whole thing way more massive and way more difficult to do and way smaller, and then it would have looked even more overwhelming. So I just made it so that these carbon groups, these carbon hydrogen groups, are all kind of together in one saying. Now, you'll notice that in the chemical equation in that top middle one, it says CH3, but then in the drawing it says H3C. That's just because I want to demonstrate that it's the carbon that bonds with the nitrogen. The hydrogens then bond with the carbon. That's how you'll actually write equations or write structures like that. Because if you did CH3 there, then you get the impression that the nitrogen is bonding with one of the hydrogens, which is wrong. So then to give an example of what would happen when you dissolve it in solution, it would become CH3NH3+, so methylammonium, and that's what that's called, methylammonium. So sometimes you'll see conjugates of amines called ammoniums. Don't get that confused with the actual ammonium, which is different. I'll explain why it's different later, but I want you to ponder on that first. So all amines are weak bases because what they'll do is they'll pull a hydrogen from solution, making them a Brønsted-Lowry base, because they'll pull a hydrogen. So basically that nitrogen will then tack on one more H to it, and then make that side slightly positive. So primary amines are the normal ones that we're going to deal with often, but just in case they come up, I'm also going to talk about secondary and tertiary amines, and then also possibly quaternary amines, but I don't think we'll ever see those because they have their own little special properties. So secondary amines are just the same thing, except instead of 2 hydrogens, one of those hydrogens is replaced with another random organic R group. Hence why now it's R1, R2 bonded with NH. Same exact thing. The real example would be diethylamine. Instead of just methylamine, it would be, it should be dimethylamine there. Again, because these are weak bases, they have to be represented with equilibrium equations. Notice that CH3 part doesn't split off at all because that's part of the actual structure of the molecule. That's not something that changes. One more thing I want you to notice is that because the hydrogen is being tacked on and you're getting a base that's added to solution, so you're generating OHs, making this more so a base because you're pulling hydrogens from it. With that equation, you have to write it as the original molecule plus water reacts in equilibrium to form the ammonium compound of it plus a hydroxide. The key part being you have to add the water. You can't just suddenly have CH3,2NH plus H plus. You need to know where that H plus comes from and how it's making this a more basic solution. Kind of like when we first did redox reactions, how that final step, when you're doing a basic reaction, that final step, you have to convert all H pluses into OH minuses so that you realize that you're creating a basic solution with this. The same exact thing goes on here. You have to switch those H pluses into OH minuses to show that now you're in a basic solution. Okay. And then that tertiary amine is just the exact same thing as the previous one, except now we've taken off that last H group and replaced it with another organic group. And then it's just the same thing. You would call it, instead of dimethylamine, you would call it trimethylamine, and then you would call it trimethylammonium. So our notes now. So it's made of a nitrogen atom and 1 to 3 R groups, which are all organic, where any remaining bonds on the nitrogen would become H pluses. I mean, that's just what we've shown. They're always weak bases, of course. The conjugate is an ammonium ion, which is different from NH4, and it needs a fourth bond to the nitrogen to make it into an ammonium ion. And then that next one, when non-organic elements bond as one of the R groups, they are also called amines, but we rarely ever see them. So instead of seeing an R group where you would just have CH3 or C2H5 or something like that, instead of seeing an R group like that, you may see an R group that has, instead of like H3C, because the total charge on that would be +1, you would see like silver, Ag, because that also has a charge of +1. That is something you can see, but we probably won't see it. That's something you might talk about in like non-organic chemistry in college, but we probably won't even see it. We'll probably just see things based on CH3s. So that next one, quaternary amines exist with positive charges. They look like trimethylammonium, but bond with something other than H+. So if you look at that bottom right one, trimethylammonium, your final thing there, instead of it being an H+, you would have like basically another CH3, and then that one would have a plus above it. That would be an example of a quaternary amine. They're very rare to come by, though, at least in our class. I don't actually know in real chemistry, to be honest. Okay, and then that critical question for you. See the relation here with NH3 and NH4 plus. NH3 is ammonia, and then NH4 plus is ammonium. I mean, you can see a difference here. Amine, ammonia, ammonium, ammonium. It becomes ammonium when you tack on an extra H. It becomes a positive. Ammonia is a weak base. It's the same exact thing. They are. So it makes it a little easier to remember amines and to remember ammonia and ammonium when you start thinking everything, when you categorize all of these in the same exact box as one another. Okay. That is annoying, but that's all the amines are. All right, now our last special condition. So this is called amphoteric. Now, the idea behind amphoteric are things that aren't defined by whether or not they're acids or bases. It means that they can be either one depending on the situation they're in. For example, water. Also bisulfite. I'm going to talk about why both of those are in just a second. So water can add H pluses or OH minuses to solution. It just depends on what other chemicals it's with it. If water bonds with an acid, it might form more acidic stuff in solution, but if it bonds with a base, it might form more basic stuff in solution. It just depends, and that's what makes water amphoteric. Now, the second one would be bisulfite, because the bisulfite can either accept another H+, because it is a polyprotic acid conjugate. It can either accept another H, or it can give away another H. And because of that, that means that it's amphoteric. It can either make the solution more acidic or less acidic. In other words, more basic. The notes just say the same exact thing I said. The main ones seen are water and conjugates of polyprotic acids. That's the main key of whether or not you're going to determine something's amphoteric. If they're asking you, oh, qualify if it's a acid or a base, and you see some sort of ion tacked onto it and it's something negative, make sure it's not a polyprotic. Because if it's a polyprotic and it's one part of the polyprotic, then you might have an amphoteric thing instead of an acidic or basic thing. Okay? So most have two equations to distinguish acidity or basicity. Yes, that's a word. I don't like that word, I'll be honest. But water always is odd because water can form both OH and H in the same exact equation. So it kind of stands on its own. But most times when you have the dissociation equations for amphoteric things, you'll see the bisulfite is the one, like the example given by bisulfite as the one that's used, where you'll have those two equations. So yeah, that is our last special